in our adventure through crystallography is called twinning. Basically, what we're going to work on today is how crystals can intergrow with one another. So twinning is the intergrowths of crystals. It's a type of complexity that provides a lot of beauty. They can be fantastic specimens to have in your mineral collection or museum collections. In the textbook, it's 226 to 234, and most of the relevant information is in that first 4 pages of the textbook. There are different types of twinning or intergrowths that can occur. The first type's not actually technically a twin. It's called epitaxis or epitaxial overgrowth. Epitaxis. It's a word you've probably never heard about before. But what we have with epitaxis is compositionally distinct growth between 2 mineral phases on top of one another. I think this is a really beautiful example of epitaxis. Let's put the definition in before we talk about that figure. So what we have is compositionally distinct oriented growth of one mineral upon another. Oriented growth of one mineral atop or upon another. In our example here, we have fluorite, which is CaF2, and it is growing above galena, which is PbS. This type of growth works because there are planes of good fit between the 2 phases. Another way to say it is that it is thermodynamically favored, and it makes it easier for nucleation to occur. And so let's just actually put those 2 notes down here. We're going to say that it's allowed. So why does it occur? Well, it's allowed by planes of good crystallographic, easy for me to say, planes of crystallographic fit. Another way to say that, maybe more scientifically, is that there is a thermodynamically favored as substrate encourages nucleation. Substrate is the bottom crystal, encouraging nucleation of the top crystal. Favored as substrate encourages nucleation. Right? It reduces chemical blocking point. And so if we were to try to draw kind of what's going on right in here, well, what I want you to do is we're going to draw 2 lattices stacked upon one another. I think I have just enough space right here to do it, so I'll give it a try. In our first mineral, let's just draw like a nice kind of cubic lattice. We're not going to do this in 3 dimensions, just 2 dimensions. You're going to draw a stack of dots on top of one another. Let's just go 3 stacks. And if you were to put lines between them all, we should see squares. I'm going to go ahead and do that. Right, nice and regular 90-degree angles. That is mineral A. Mineral A provides a substrate for mineral B to grow upon. So what we're going to do here, and I'm just going to kind of cheat and go ahead and draw mineral B lattice first, and then I'll put dots in later. Mineral B has a different orientation in its crystal lattice, but the spacing is just right to fit the bottom one. So let's actually go ahead, let's put a line across here. We'll make this be some kind of like monoclinic crystal. These were supposed to all be the exact same size. I shouldn't have whispered that, I guess. All right, so we're going to put in now our nodes. Right, and the point that I'm trying to make here is that in B, the spacing in the nodes in B is equal to the spacing in the nodes in A, and it just allows for that nucleation to occur. That's one of the types of intergrowths that can occur between crystals. We call it epitaxis or epitaxial overgrowth. Something similar but different is called parallel growth. Parallel growth involves the same composition. So parallel growth, the textbook I think defines this as aggregate of the same mineral with same crystallographic orientation. So basically what happens here is that we look like we've grown more than one crystal, but it is actually just one. And we'll write that down too. So what we have here is we have an aggregate of same mineral with same crystallographic orientation. Like whenever you see crystal clusters, that's what you need to be picturing is going on here, parallel growth. They're all quartz, but the quartz is all growing in the same direction, but it makes different peaks and spires. So we'll just say something like, we'll make a little note here like crystal clusters do this. Or we could say something like looks like more than one. But it is actually just one. There's a nice figure from the textbook that shows this. We could have put a bunch of pictures in of real minerals as well, but I like this picture as well, a lot. So what we have here is one crystal of quartz. In this area, if you only looked like below this line, you'd be like, oh yeah, that's just one crystal of quartz. But as it goes towards its termination, it breaks up into a whole bunch of different little crystals. Each one of these actually will have the lattice perfectly aligned with every other one of them because it is the same crystal, just with multiple terminations. This is called a scepter, and not just quartz does it, a lot of other minerals do it as well. Here's an example of barite. All right, and it's parallel because look, I mean, you can imagine like the lattice is parallel in every single one of these. And if we were to look at it microscopically, we would see that they're all parallel as well. All right, so now let's get finally to where we're really trying to get to today, which is the concept of twinning. The definition for twin is as a symmetrical intergrowth of two or more crystals. Symmetrical intergrowth of two or more crystals. Let me put a picture up right off the bat of quartz showing a symmetrical intergrowth of two different crystals. This is not parallel growth now in this example, right? The lattice is not going in the same direction. They're going in different directions. And if you were to put like a mirror plane right here in the middle, maybe you could trick yourself, well, not trick yourself, because it actually is. There's a mirror plane here, and we have one lattice going that way and one lattice going the other way, and they're intergrown with one another. And that's a twin of, oh yeah, we need to say two more crystals of the same substance. Let's draw this. Okay, we got to do this carefully. We're going to try to draw a penetrative twinning of two different crystal lattices. Well, it's the same lattice, but they have different orientation about a mirror plane. To do this, I'm going to draw a series of rectangles. If you want to, you could just like fast forward this as I'm struggling through it. So there's our unit cell that we're working with. All right, we're going to put nodes. We're doing this in 2 dimensions. I'm going to do another block down here, another block down here. Really, it's the final product of this drawing that you want to see. And for me to do this right, I'm going to have to go a little slower than what I'd like to. It's going to be a step-wise here, because I need to put in a twin plane that is about this step. So I'm going to put another one here. All right, let's see if this works. All right, so here is our crystal lattice, and we're going to have a twin plane that shoots across. Okay, this is going to be the hardest one for me to draw. We have to just connect those dots. Okay, we've connected our dots right through there, and this is a mirror plane that you can't really see, but it is within the crystal lattice. And it's going to reflect this lattice to another lattice right here. So one way to maybe show that would to go, okay, so we have this line, and it's a mirror plane, so that means this line needs to go like so. And it goes, this is going to make a kite shape, right? So we have this triangle, we have to make the triangle on the other side. Comes down like this. And we can do another one right here. There's here to here, like so. And we can repeat this whole structure up here on the top. So that's what I'm going to try to do right now. Is this working for you? Can you see what I'm trying to do? We have taken this brick pattern and we have mirrored it across this twin plane of a mirror to produce another. And if we were to continue the blue down, it would actually penetrate into the black area. And if we were to continue the black, we would also penetrate into the blue. Right? It gets a little complicated here, but the lattice allows it to do that because the spacing is just right. And so we're just going to make a note here, and we're going to say that the lattice directions are related to one another. Related to one. Okay, I'm lagging out a little bit. One another. Maybe some more examples would actually help kind of drive this home. There's about 4 different types of twins that I want to cover right now. There is a series of growth twins, and then there's a type of deformation twin. So we're just going to march through these. Growth twins. There are 1, 2, 3, 4 types of growth twins. The first type is called a contact twin. That's what I showed with quartz just above, where there's a mirror plane. So we could say something like about a mirror and draw up here like quartz and the sketch that we just did. There's another type of growth twin that's not about a mirror, but it's about an axis. And this is called a penetration twin. Sometimes these are called cyclic, when there's like a lot of them repeated. And so we're going to penetration twin about an axis, and we could put, like, if we put an axis right here and we drew one crystal and we wanted to rotate about that axis and do another crystal intergrown with it, well, you might get something like this in the shape of a cross. And that happens quite a bit. Here's an example that it would actually be called cyclic, where the shape, this is a mineral called chrysoberyl. When it's a gemstone, it's called alexandrite, and it's stunning. The rotation axis is here, and we can take one crystal and repeat it 1, 2, 3, 4, 5, 6 times. Right? That's a cyclic or penetration twin. A third type, this is probably the hardest to visualize, it's when you have an inversion. So the inversion acts as a twin rotation. Boy, these had a really nice name, contact twin. This had a really nice one too, penetration. This has a terrible one. So we'll just call it an inversion twin. An inversion twin, this is the best example I could find. This is of pyrite, and what we have here is like a cube of pyrite that has been rotated around upon itself with another cube of pyrite, creating this more unusual shape. These 3 types of growth twins can all be organized together as twin laws. So this is what we call them. We call them, so like a contact twin is a twin law. And they're twin laws that are related by a symmetry element that brings into alignment. And we'll put that here. We'll say that a symmetry element brings crystals into alignment. or would bring them into perfect alignment, right? Like this crystal here would be brought into perfect alignment with this one with our rotation of 60 degrees. Now there is a fourth type of growth twin that's different. It's not, doesn't have a symmetry element like that. It's called a polysynthetic twin. And the story with a polysynthetic twin is that these are closely spaced, repeated growth twins. Closely spaced and repeated growth twins. The axis like of a mineral is flipped, let's say, by 180 degrees, and as each progressive layer of a crystal gets formed. And we might make a crystal, here's an orthorhombic crystal in 3 dimensions, and we were to break it open, and let's say this is it, we're going to say that we're looking down on a cleavage face, right? Because the cleavage face allows us to see the breaking of the crystal. And what we might see are a bunch of lines, and these are supposed to be perfectly straight. They're not supposed to be squiggly at all. They're supposed to look like mechanical grooves across this face, like a machine made it, and then they'd be across this face as well. Oh, that's a way better drawing than I did at the top. So, and what they look, so we're going to say they appear as striations on cleavage faces, basically on planes of breakage. It's really important in plagioclase. So I'm just going to put a little star right here because plage becomes, oh yeah, plage, the cool way to say plagioclase, or perhaps the lazy way to say it. Do I have a picture of this? Sure, I'll show you a picture of polysynthetic twinning on plagioclase. Here's an image that I took. I didn't even steal this from anywhere on the internet, although people do like, the internet resources are all about education, so we can do it. So can you see these grooves that are aligned parallel to this arrow? They're very regular. They're very closely spaced. Well, that is not man-made. That is one of the best ways to identify plagioclase, is to look for the presence of polysynthetic twins on its face. Okay, and then the last type of twinning, this is going to be big B. Big B is not for growth twinning. This is for deformation twinning. Deformation twinning means you apply a force to a rock. You will deform the lattice sometimes in a way that is highly regular. This is sometimes called mechanical twinning. And the definition for this is lattice is bent by applied force. There are many different geologic processes that have all sorts of forces acted in them, sometimes very powerful, and they can deform and bend minerals. It's probably like how the whole field of metamorphic rocks work, right? And these tend to end up actually looking like polysynthetic. So let's even put that here. They appear polysynthetic. And you may even call them polysynthetic deformation twins, and no one will get mad at you, because in the rock or in the mineral, you will see these closely spaced things, but they don't form by growth. Instead, they form by deformation. And so you'd want to look for evidence of that. How is this formed? Let's make a drawing of how this forms. So put a bunch of dots. Let's say I think we need 5 dots, and we're going to do a sequence because we're making a lattice. This is our undeformed lattice that hasn't had any force or shear applied to it. But if we were then to take powerful geologic forces and shear it like this and like this, right? Really torque it up, we would create a resulting pattern that would be, okay, I'm going to put the 4 middle dots in first. What would the dots look like on either side of that? Well, these dots below that line got pushed to the right, and so they would be angled like so. And the dots to the, did I mess that up? I might have messed it up. Well, anyways, all I wanted to show you is that you're gonna, I might have messed it up with the arrows there a little bit here, guys. And since I'm doing this live-ish, I'm not sure I can fix it. This would be an arrow in this direction and an arrow in this direction, and boom, we got along this plane, there'd be a deformation band, and we have to strain the lattice, and it might create banding that looks like that. Whoa, now to deflect you from my somewhat unskilled sketch, I'm going to show you a thin section of a mineral called quartz. All right, so thin section is this. Did I say quartz? I'm out of my brain right now. Focus up. This is a mineral called calcite. Calcite has a hardness of 3. It's rhombohedral. It's a chemical formula of CoCO3. Anchoring myself with confidence with these. And when calcite gets deformed, it will break with a rhombohedral cleavage. So here, if this is our chunk of calcite, it will start to break and deform with a rhombohedral cleavage. And we can see right here, do you see that pattern of lines? Those lines, specifically like the thickness here, like right there, that is a deformation lamellae. And that's a deformation lamellae. Lamellae just means like sheets of paper. And it's just a technical way to say the layering, right? We can see it in this crystal of calcite here. So that right there, that would be an example of a deformation twinning that's going on inside of deforming calcite. Well, I'm glad I was able to show you that. Let me show you one last one, since I like diamonds, and everyone kind of loves diamonds. Pink diamonds are colored pink by deformation lamellae. A pink diamond's worth like $600,000 a carat, even though a white diamond is about $5,000 a carat. So it's a precious thing. And the thing that is making the color are these bands right here. And those bands are deformation twins inside of the carbon-carbon lattice of diamonds.